Okay, so what happens when this lithium hydrogen carbonate goes into the water? Second?
Ionizes.
Immediately, since there's a group 1 metal there, the lithium, that's a solid, turns into lithium ion and hydrogen carbonate. Is that lithium going to do anything in the water?
Mm-hmm.
It will not. Why is that?
Because it's a cation on a strong base.
Correct. It's the cation of a strong base. Nice work. So it can't do anything. It can't take a hydroxide away from water or an H away from water and change the pH. So that's out. But what about the hydrogen carbonate? That's the anion of what? A weak acid. So weak acids like to be in what form? What'd you say?
Oh, I said healthy.
You said healthy?
Yeah.
I don't
Being funny.
have any idea what that means.
It means it needs everything.
It needs everything?
It wants to fall.
It wants to be as a molecule, right? It wants to have no charge. So it would like to be carbonic acid. So since there are water molecules floating around, the carbonic acid is strong enough, or the hydrogen carbonate is strong enough to yank an H off of water, leaving an OH. So if you put baking soda in water, what's going to happen to the pH? I know this isn't baking soda, but it's almost baking soda, right? It'll go up. Yep. I have more hydroxides, so then my pH is going to go up. Okay, so this question is related to the next question, and the fact that I want you to realize that when you add a small amount of an acid or a base to water, how dramatically the pH changes. And then when we do the exact same thing to a buffer, how it doesn't really change at all. So this first one, we've got 2 molar, 15 milliliter of 2 molar sodium hydroxide. And I wanted to know that the pH is, so I need to take the negative log of either the hydroxide or the hydrogen ion concentration so I can calculate out the pH. So I need moles and I need liters. So I'm going to do the mole part first. So we've got 2.0 moles of lithium hydroxide per liter, but I've only got 0.015 liters. And so I end up with, what is that, 0.03? mole of hydroxide. And then if I take that number and I divide it by, why am I going to divide it by 0.5 liters? Where'd that value come from? Yeah, so if I take my 15 milliliters and my 485 milliliters, I get 500 milliliters. And so that's half a liter. So half a liter there. And so I got so that's the amount of hydroxide that's been added to this water. You okay? Okay. So if I take the negative log of 0.06, I'm going to get I get 1.22. What did I just calculate? I calculated the POH. How do I know that this is the POH? Because I added base, so I just took the calculation of the thing that came off, which was the OH, so that's my POH. So then my pH is going to be equal to what? 8? 12.78? So is that a big change in pH? It was 7, now it's almost 13. We're looking at over 1 million. The pH changed by more than 5 orders of magnitude. So you're looking at a million change in pH. Million times more basic. You right there, Gento?
Where did you get the subject?
Where did I get the what?
Pure. Oh, water. Okay.
It's water, yeah. Okay, so now we're gonna, so I had a million change in the pH if it was just water. So what if I have this citric acid buffer? So the first thing we're going to do is figure out what the pH of the citric acid buffer is before I add the sodium hydroxide or lithium hydroxide to it, and then what it is going to be after. So initially, I'll just write the pH is equal to, what's the pKa? Somebody have that? 3.14 plus log of 0.2 or 2.25 divided by 0.22. Plus the log of 2.25 divided by 0.22. So I got a pH of 4.15. Okay. Does that 4.15 number make sense? What would the pH of the buffer be if I had equal concentrations of salt and weak acid? No, 3.14. If I had equal parts of salt and acid, that would make the fraction equal to 1, and the log of 1 is 0, right? We okay with that?
It would be like
It would be 3.1, no, it would be 3, wait, what?
2.15. Like, is that what you're saying?
If the two numbers on the top and the bottom were equal to each other, then the pKa is going to be what the pH is going to be equal to. But why is this higher than the pKa?
Because there's a difference.
So why is it higher?
Because the bottom number's small.
So
Uh,
what's the bottom number?
That has-
The denominator is the acid. So when I made this buffer, I put a whole heck of a lot more salt in it, right?
yeah.
And what's the salt of a weak acid do to the pH? First question, this homework.
It makes it go up.
It makes it go up, right? So what we had is the weak acid was bringing the pH down, but the salt of that weak acid brought the pH up a lot more than the weak acid brought it down. Does that make sense? If the top and bottom were both 0.22, then those two numbers would cancel out and the pH would be 3.14. But I have a whole bunch more of the salt in there, and the salt raises the pH. It's actually more than 10 times what it is, right? Value-wise, 2.2 to 0.22. So then it's actually more than an entire pH unit. Do we see that? That's a pretty big difference between 3.14 and 4.14, right? How much of a pH difference is that? How much of an acidity difference is that? 10 times, right?
Yeah.
Because this is the logarithmic scale. So because I put so much of that sodium citrate in there, the pH is actually an entire pH unit, which is 10 times the basicity of just the citric acid if it would have been equal parts of that in the salt. Okay, so I've got this pH and it's sitting here at 4.14, and then I'm going to drop this lithium hydroxide in here, and we're going to see how much the pH changes. But I need to know what's the most important part of this? Knowing. What do I need? What's the most important thing to know about all of these things that are in this water?
The base and acid, everybody.
I need to know how many of them that there are. What do I mean by that?
You mean out here lithium hydroxide?
I need to know how many OHs got put into the water. I also need to know what? I don't care about the lithiums. No, don't care about the volume. if there's enough buffer. How do I know if there's enough buffer? I need to count them, right? I need to know exactly the number of citric acid molecules and exactly the number of the citrate anions I have in my buffer solution. And then I need to know how many OHs that I'm going to put in, right? Because the buffer will eventually fail if you do what?
If they've already attracted enough OHs, they run out.
Yeah, if I run out of citrates or I run out of citric acids, any more acid or base added to it's going to dramatically change the pH. So I actually need to know how many of each of the three components I've got. The two pieces of my buffer, my weak acid and my salt, and then how much of whatever it is I'm adding, an acid or a base. So I need to know exactly how many of them there are and what unit do we use to figure out how many of them there are. Moles. So I need to count them, and I do that in this case since I was given concentrations by just taking the concentration and multiplying it by the volume. So how many citric acid molecules I have, I'll go 0.22 moles per liter of HA, and I'll multiply that by 0.485 liters, and that'll be moles of the weak acid. And then I've got 2.25 moles per liter of the anion, and I have the same volume of that. And I'll just do the math down here again so we've got them all. I've got 2.0 moles of OH. I'm going to add to this per liter, and I had 0.015 liters OH. And so that's going to equal 0.03 moles of OH. And it's going to equal 0.22 times 0.485. 0.25 times 0.485. So I got 0.1067 and then 1.08 moles HA. So those first two things that I have highlighted are the two things that are sitting in the buffer, right? I have just counted how many weak acids and how many salts I've got. And then I'm going to throw that third thing in, the hydroxides, and figure out how much of the buffer pieces are left. So I'm going to have HA and A negative, and initially I've got 0.1067 here, and I've got 1.08 here. And then they're going to change. The change, so this hydroxide is going to react with what? The weak acid or the salt? So I'm putting in OH. Which of these two things is the OH going to react with? What do bases react with? Acids. Bases react with acids. Tell me a really good reason why the OH is not going to react with the citrate anion. A really good reason. How about the fact they're both negatively charged? So is there any way for them to react with each other? No, there's no way for them to react with each other. So that tells me who gets subtracted and who gets added. I added a base, so what goes up? Well, of these two things here, what goes up? I added a base. So the base goes up, and the base in this case is the salt, right? So it's going to go up by 0.03. I added a base, so what's going to disappear? The acid.
When you said that they're both negatively charged.
The hydroxide and the citrate anion. What happens when the sodium citrate goes into the water? What's the sodium do?
Well,
Falls off immediately, leaving the citrate anion, right? Just like on the first question on the homework, the hydrogen carbonate was negatively charged. Okay, so what do I got left here? I got 1.11 And I've got point, 0.767, is that right?
How did you decide that one was a plus on and one was a minus on the page?
That's what we were just
I know.
saying.
Didn't you just say it again?
No, you tell me what we just said.
I were talking about when you bind it with the acid or with the citrate.
Okay. Let's not think about this math for a second, okay? What do you have? What did we start with?
You mean the buffers?
Yep, tell me what we started with.
With citric acid and sodium citrate.
I have a container that has citric acid in it, right? And it's got the anion from that citric acid, and in this case, some sodiums that are floating around, okay? We couldn't care less about the sodium. It's a spectator ion because it's the cation of a strong base, so it can't do anything in this particular instance. So those two things are floating around, right? And to this, I add some hydroxides. So what's going to happen?
It's gonna pull off the acid.
It's going to take this off of here, right?
Right.
And turn into a water molecule. So what did I just do to this A? I disassociated it from its H, right? So basically, I just made some of that, right?
Okay.
I turned my weak acid into my salt, because that's what happens when you mix an acid and a base together. I make a salt and water. Well, there's my salt, and there's my water, okay? So why did I decide?
That's why you said the A negative is gonna go up.
That's why the A negative went up.
Okay.
And that's why the acid went down, because that's the thing that was consumed to make sure that the pH didn't change. All right, so then we need to answer the final question, which is the pH of this new, after I've added, is going to be the pKa, which was that 3.14, plus the log of, now it's going to be 1.11 divided by 0.767. And so my pH is equal to 3.14 plus log 0.111 divided by 0.767, close parentheses, equals. Yeah, totally my bad. That's a 0 right there. Yeah. I'm like, wait, this number totally doesn't make any sense. I put a 0 in there. There we go. So my pH after this addition is 4.30. So before, when I added the pH, this lithium hydroxide to the water, how much did the pH go up?
12.8.
So more than 1 million, right? More than 5 orders of magnitude. And now I added it to it, and what happened? It went up 0.15 hundredths of a pH unit, so it stopped it basically. Okay.